It's an enormous pleasure to be asked to talk in this lecture series. As I hope I'll make clear in the talk, there's a sense in which things have moved rapidly in the past 10 years or so, with much more interest in open science and reproducibility, despite there being fascination around these topics for some time. But it's as if there's now a momentum behind attempts to improve science. And I see this lecture series as part of that. And I really couldn't say no when I was asked to contribute, because it's something I am really pretty passionate about. And in particular, the topic of registered reports, which for those of you not so familiar with them, I'll explain what purpose they serve and how they work. And also a few comments about my own experiences of the benefits and potential drawbacks. And then I'll leave time so that we can discuss what it's like in reality, in case any of you are encouraged to attempt this particular format or have thoughts as to why you shouldn't. But if we start at the beginning, there's the question of what problem is registered reports trying to fix. And it's this problem that's really grown and grown in visibility in the past 10 years, with more and more people being concerned about particularly what's called reproducibility of science findings. So Johnny Ioannidis sprung on the scene in the medical field with a paper that had a very provocative title on why most published research findings are false, where he argued that the way we're doing science is bound to mean that many findings are just not going to stand up if we try and replicate them. That was more of a theoretical paper, but subsequently this paper by the group in Nature on the psychology's largest reproducibility test, headed up by Brian Nosek, actually demonstrated empirically what the problem was. That is that they tried literally to replicate some studies that were in the mainstream psychology literature and found that really only about 35% to 40% of cases, depending on how you defined it, could be replicated. And our statistical methods should make that much higher, because we're really typically saying when we publish something that we've done statistics to show that this is an effect that should be reproducible a much higher percentage of the time than that. Now, it's not just psychology. Sometimes people think, oh, it's just psychology, but in fact, there's very few areas of science which don't have these problems. So there was this paper by Bustin in biomedical research who said that there was really growing evidence that many articles published in that field are wasted, in the sense that they come up with results that nobody can reproduce. And this has got practical implications for the pharmaceutical companies who then try and build on the back of research done in universities. So this is a much cited graph, this pie chart from a study done by Bayer. The details of it are unfortunately not really all that transparent, but basically this was a drug company trying very hard to just get a sense of how reliable research was, because it costs them a lot of money if they decide to try and develop a drug because somebody's found an interesting thing, and then find that they can't actually replicate the basic initial finding. And they've claimed that that was true for about 64% of the studies they looked at. And this is not just bad for science in terms of developing new things, but it's also wasteful, and that was a point made by Bayer. And then this last article I've got here in the Lancet is also just focusing on the waste of people doing research, which is not reproducible or not necessary sometimes. There's various reasons why we get research waste, but this Lancet piece was very much focused on the need to try and reduce the amount of funds that are wasted. Now, why have we got poor reproducibility? There's a whole host of factors, and I shall talk a little bit about later about what one might call structural factors with how the scientific system works, and incentive structures in science, which certainly play a part. There's other factors I'm interested in are to do with human cognition and the way we think, which I think is often at odds with doing science well. But the other thing that I think is really very important, certainly in the field of psychology and many related fields, including medicine, biomedical studies and biological studies, ethology and so on, are these factors to do with how we do our science in terms of research design and what gets published. And so I've talked about in this little comment I had in Nature in 2019, what I call the 4 horsemen of the irreproducibility apocalypse, which are publication bias, low power, p-hacking and harking. And I'll say a word about each of them to make it clear what I mean by these terms and try and demonstrate why they're so problematic and how they contribute to poor reproducibility. So the first and the most obvious one is publication bias. We expect science to be cumulative, and so we expect if we get a result that it will reproduce, but there's a real problem that if the only things that get into the research literature are positive results, we get a very distorted picture. And we've known about this for many years. So 2 psychologists who commented on it in the 1970s were Greenwald and Rosenthal. Greenwald talked about prejudice against the null and argued that the research publication system may be regarded as a device for systematically generating and propagating anecdotal information. How so? Well, it's what Rosenthal called the file drawer problem. This idea that if you do a study and the findings are non-significant statistically, it doesn't get published. Either because the researcher themselves decides it's not very interesting and they put it in their file drawer, or because the journal editors are not interested in publishing it. So even if you try and publish your null, non-significant findings, then you have difficulty. Now, what you might think, well, this doesn't matter. We don't want to know about all these boring findings. But if you think not just about individual studies, but you think about science as a cumulative exercise, you can begin to see why we have problems. So here's a very nice graphic that shows in one particular field how bias can really mislead us. So here the authors looked at studies that had been registered on effectiveness of treatments for depression. So they took a particular time band, and the thing about medical studies is these days they do have to be registered, so you are able to see which studies were registered but were not published. And what you see here is that we start off with about half and half. The trials that they call negative trials are ones with null results. So about half the trials that were done obtained null results, and the other half obtained some positive result. But if you then look at the next histogram coming along, you see that about half of the negative trials have disappeared, and this is publication bias. These are studies that were done, that obtained a result, but were not published, and as you can see, virtually all the positive trials were published, but only about half of the negative trials. It gets worse, and I won't go into details about these other things because they're less relevant to today's talk, but you then get further bias where people do a study that obtains a null result but report it in a way that is misleading, maybe reporting only on certain outcome variables rather than others to make it look more positive. And then there's the phenomenon of spin, where something is really just described as if it was a positive result when it wasn't. And by the time you get to this final right-hand chart, you start to see that the red dots are very, very few of them have survived, and they're very small. And this final set of bars is how frequently the work is cited. So the bigger the circle, the more frequently it's cited. So even if this non-significant finding makes it into the literature, it's then forgotten. Now that's a different problem from the one I'm focusing on with publication bias, but you begin to see what a problem we have if you think of science, that science should be cumulative, where the reality is that only about half the trials that are done give you a positive result. But by the time we've been through this whole process, it looks overwhelmingly as if almost all studies give a positive result. And that's what we'll see cited in the literature. So we have a problem, which I think is only very evident when you start to think of it not in terms of individual studies, but in terms of the literature as a whole. Now, there's a further problem, and I'll put together p-hacking and harking because they are like terrible twins, which is very similar, but whereas publication bias is to do with bias in what gets published, p-hacking is bias in what gets analysed and reported. And so it can be equivalent in some cases to this sort of spin or outcome bias, reporting bias that you see. But it takes a number of forms, but it's basically what you get if you do a whole set of analyses but only report the ones that are congenial, the ones that give you the magic p less than 0.05. Now, again, often people think, well, what's wrong with that? We want to know about the interesting results. What's wrong with this is it leads to a massive inflation of the error rate so that you get a lot of false positives if you don't apply appropriate corrections for your statistics. And let me show you an example. Here we've got some data that is just simulated random data. So there's really, we know because we've simulated the data, there's absolutely nothing going on here. But I've simulated data from, I think that's 16 or possibly 20, I can't count for, but 16 variables. And let's just say that's the score on the y-axis is how much memory improves after you've been given a drug. So you might be a pharmaceutical person interested in trying out a whole load of drugs and finding the ones that are going to be most useful. So you generate your data, and the typical thing that then happens is that you look at results like this and you think, well, we've got two significant results there, compound G and compound J are looking pretty good, so let's go ahead with those. But the problem is that those little asterisks corresponding to the conventional p-value are very misleading if you look at that number of statistical tests. The key question is whether what your hypothesis actually was. The typical p-value associated with a single comparison will give you the answer to the question of whether you're significantly different from chance if your hypothesis is that that particular compound enhances memory. But if you've tested 16 compounds and you don't really care which compound is which, you're just interested in whether any of them enhances memory, then that p-value is very, very misleading because the null hypothesis then, the probability of a false positive, is the probability that none of the null hypothesis is the idea that none of these 16 compounds enhances memory. And to work out that probability, you take 1 minus 0.95 to the power of 16, which is 56%. So in other words, you've got an over 50% chance that just randomly, if everything is just noise, at least one compound is going to look significant. So this is a very, very difficult point to grasp. People really battle with it because most people have been taught that you look for something that's less than 0.05 and it's like a measure of importance or effect size. The key thing to realize is that the way you interpret a p-value is very much determined by the context in which that p-value was gathered. And that comes down to what your real hypothesis is. And if you're testing lots of things all at the same time, without any concern as to which thing might pop up, so you've got lots of outcomes, you do need to correct. And I'm sure many of you will have heard of things like the Bonferroni correction that you can apply. But there are other corrections you can apply that are less stringent than that, if, for example, you've got correlated outcomes. But you do need to apply a correction if you're doing this sort of looking for anything that might be there. And the real problem then is that if you're just sort of generating your hypothesis that these two substances, G and J, are the important ones, having seen the results, you're then using the same data to both generate the hypothesis and test it if you don't correct your p-value. The fact that you shouldn't do this was recognised way back in the 1950s, and people have talked about it since then. But it's often just not understood because it's complicated, and understanding probabilities is complicated. And I try and explain it all the time to people, but it's really hard to grasp. This paper by de Groot is really worth reading, and it was neglected for many years because although he was an extremely eminent Dutch psychologist and chess grandmaster, I think, as well, he wrote in Dutch. But it was translated in 2014 by Wagenmakers and colleagues, and it's really a very nice explanation of why you've got to be very clear what your hypothesis is. And if you start building your hypothesis as you go, having looked at the data, how your entire edifice of logic can be completely scuppered. But this is what people do all the time in many, many fields of science, because they really just don't understand this. And if people tell them about things like using corrections, statistical corrections, they think that that's just a bit optional and it's statisticians being a bit difficult. But they see that p-value and they believe it. This is what you've got to sort of somehow not do. The problem with p-hacking is of course pulling out the p-values that look good and focusing just on them. If you do that and you don't even report the other things that you did, then it's totally undetectable. So if you read a paper by somebody who says, well, we looked at these two compounds and they gave very good results, but they don't actually tell you that they were 2 out of 16, you have no way of knowing that there was p-hacking. And again, it's very hard to know, but unless you have a study pre-registered and so you know in advance what people were going to do, you can't actually tell that this has happened. And then you can give much more confidence to results which shouldn't have confidence placed in them because they're really pulled out of a huge number of possible results that could have been reported. And harking was talked about, again, a long time ago in 1998 by Norbert Kerr, again, an eminent psychologist, and that stands for hypothesizing after the results are known. And that's what tends to go hand in hand with p-hacking, that people look at the results and then say, well, this would make sense of the results. Here's my hypothesis. So again, a lot of people say, well, isn't that what a good scientist does? They look at their data, they see what's in there, they're exploring for something interesting, and then they notice what's really interesting. The answer to that question is yes, but you need to be very clear as to what you predicted and what is new exploratory findings, and make that distinction very clearly, or you will mislead yourself. So harking, if you had a study like this, and you had no prior predictions, but on seeing the results, you wrote it up as if you planned to only look at G and J, that would be harking, and that would be very misleading. Now, it doesn't mean you can't report this, so it would be perfectly okay to say you observed this association in an exploratory analysis and that it suggested a new hypothesis that you might want to then test in a new sample. So you can formulate a hypothesis on the basis of data like this, but what you can't do is formulate and test the hypothesis on the same data. And it's not okay to pretend that you predicted the association if you didn't, and it's really, really not okay to only report the data that support your new hypothesis and just pretend that the other tests weren't done. Nevertheless, people have been advised explicitly by very senior figures in the field that this sort of harking is exactly what you should be doing. This is a now notorious article by an eminent psychologist, Darrell Bem, which was written as a guide for the beginning social scientists. In fact, there's an earlier edition with the same advice in it, but this was 2004. Who explicitly advocates harking. So he says if you're going to write an article, you could write the article you planned to write when you designed your study, or the article that makes most sense now that you've seen the results. Rarely the same, and the correct answer is B. And then he talks about how you should look at your data from every angle, look at different sexes, make up new composite indices, etc., etc. Go on a fishing expedition. Now, this is just what you should not do if you want to get replicable results. P-hacking this isn't the only way that p-hacking works, with lots of outcomes and you just pick the one you like. That's a very common one. But there's also things like removing inconvenient outliers to nudge your result into significant, or adding covariates post hoc, or dividing your data into subgroups. And I'll just show you how that works. This is a beautiful paper by Gelman and Loken, who talk about p-hacking and fishing expeditions as well as other things. But what people remember about it is that this lovely phrase, the garden of forking paths, which is referencing a short story by Borgeth, which is all about, how one's future is, little decisions are made that you end up in one place or another depending on what exactly happens at a particular point in time. This is just a fictitious data that I made to illustrate this, where you've got a large population database, and let's suppose we're interested in ADHD, attention deficit hyperactivity disorder, and handedness, and you've got this big population, and you test whether there's a difference in handedness between those who are ADHD and typical. You don't find anything, but then you sort of make a decision to go and divide up between older and younger children, so this O versus Y bifurcation takes place. And when you go down that path, you may find that the younger subgroup, it's all looking a bit more promising, so you're going to focus on them. And then you find that you've got two measures, two different handedness measures, a skill measure and a preference measure. And so you decide that you're going to focus on the skill measure. And then you think, well, it looks even better if we just look at females rather than males. So you can see we're progressing down these forking paths, and at the end of the line you come and make a distinction between whether the child comes from an urban or a rural background, and way-ho, you're very happy now because you've got a significant result. But the problem is that every time you go down one of these forking paths, the number of potential comparisons you could be making increases. And instead of evaluating that final step with P of 0.05, you should really be again correcting from all the comparisons that you could have been making, unless you had a priori hypothesis that this was the path of interest. Otherwise, if you would have been equally satisfied to find a significant result at any point here, you really would be needing to correct for the fact that you did 16 implicit comparisons. But it is implicit, and so people don't even realise they're doing this when they start dividing data into subtypes and then getting excited by p less than 0.05. The problem is exacerbated because we now can easily gather these very large multivariate databases. We can easily do complicated statistical analysis over and over again. And so people often will be doing exploration of big databases, but without realizing that they're not really hypothesis testing, they're exploring and then often unaware of the number of hypotheses that they're looking at. If you've got p-hacking and an ideological agenda, it's really bad. Here's an example of how badly it can go. So this is the notorious Andrew Wakefield, who found a link between autism and vaccination, or claimed there was such a link. And that idea has been impossible to kill, goes on and on and on. And so what you get are things like this, where somebody found a big database, but decided that there was a link between the vaccination and autism, provided you looked at a particular time point, particular age of vaccination, and you only focused on young African-American boys. So you can see they've gone right down the forking path. They could have gone in all sorts of directions, and they found something, and then they claim there's a cover-up because this hasn't been reported. So absolute disaster if you're not aware of what you're doing. So again, huge risk of this type 1 error. But we can also worry that there are situations when there's a risk of type 2 error. So if we're interested in, for example, a new intervention, or indeed a risk factor for autism or something, on the one hand, we don't want to turn up things that are untrue and are just false positives that have arisen by chance. But we also have the problem, we want to guard against type 2 error. We don't want to miss things that are really there. And that brings us to the fourth horseman, which is low power. again, been written about for years, and people have complained for years that we do studies that don't have sufficient power because they just haven't got often enough cases, but they're just not capable of showing an effect that's really there with any likelihood, because the sample sizes are often too small, although sample size isn't the only thing that determines power. So Jacob Cohen wrote about this. He wrote a whole book about it, and in psychology and medicine this is now, I think, more recognised, but it's still the case that this quote by Newcomb from 1987 still holds true, that people will do small studies with little more than a blind hope of showing the desired effect. But then you do the study, and if you do get a significant result, you'll submit it for publication, even though it's hopeless. So this is yet another problem. Now, none of this is new, as this is what I've been at pains to show you some of these old people in the literature really talking about this. And so why haven't things changed? Well, this is in part because of this incentive problem that I mentioned earlier. Chris Chambers, this is a slide of his, so we're going to say more about Chris and his ideas on registered reports, but he's pointed out there's a complete disconnect between what's best for science, which is that we should have transparent, high-quality research, and we should get published regardless of outcome, provided you've done a well-powered study to investigate an important question. We should know whether the results come out negative as well as positive. I mean, if you're thinking of things like drug trials, we want to know what doesn't work as well as what does. But what's best for science is producing a lot of so-called good results. So, and that typically means statistically significant results and things that are very exciting looking. And so he's shown this, I don't know where he got this cartoon. Oh, Dario Battisti is the author of this wonderful cartoon, but it's somebody fishing from their computer. But he says you've got, as a consequence of these pressures, you've got publication bias, you've got significance chasing or p-hacking, you've got harking, lack of data sharing because people don't want to take the time to share their data, so it can't be checked, low statistical power, and he also mentions lack of replication. People are not encouraged to actually replicate findings. It's seen as a bit boring. Now, given that this has been going on for such a long time, you might say, well, why is it now making headlines only really in the past decade? Bustin in 2014, who was the man who wrote about the biomedical problems, he says it's really striking for just how long there have been reports about poor quality of research methodology, inadequate implementation of research methods, use of inappropriate analysis procedures, as well as lack of transparency of reporting. And all of these have failed to stir researchers, funders, regulators, institutions, or companies into action. Now, I'm more optimistic, and I think a lot of change has started to happen since he wrote that, and I think there has been a number of things that have happened. One is that there have been a number of meta-science studies, so these are studies that actually are just quantifying the problem. I mentioned previously that study by Brian Nosek, where they actually explicitly replicated a load of psychology studies. There have been other attempts like that, including a very interesting replication project on cancer biology, which showed difficulties replicating studies in that field. There's also concern from research users who've got more vocal. So doctors and patients are starting to complain if they find that people are publishing stuff that just isn't replicable and reliable, and they're trying to treat patients on that basis. Pharmaceutical companies, we've already noted, are getting concerned that they're just wasting money trying to develop drugs if research isn't replicable. The third thing that I think has made a big difference is social media, which often people say what a terrible thing social media is, but for this sort of problem, it's often the only way to publicise the problem and to shame, quite often, people into taking action about it. So what you need is people able to call out bad behaviour when it occurs, and even if it's not bad behaviour, even if it's just sort of what are called questionable research practices, there's been much more discussion of it on social media than you would get in the conventional journal articles. And it moves much more quickly and there's much more chance for debate. So it's not always civilized debate, but it has at least brought this problem to the fore, and it's given voices to people who may be damaged by the problems in science, who are not just the users of research, but quite often junior researchers who are trying themselves to build a career and are then finding they're subject to these perverse incentives and are told that they have to work in a way that they're not really very comfortable with. So how can we fix it? There are a number of fixes. Again, there's no one single fix, but I'm here to talk today about registered reports, which I think can go a long way towards fixing it. Now, funnily enough, the idea of the registered report is also very old. So I'm going to talk about Chris Chambers and his initiative with registered reports, which was much more recent. But I was astonished. I was reading, this is in a book. It's very hard to get hold of, but I just happened to find this old book, which was a very interesting man, Michael Mahoney, social psychologist, writing about issues about scientists and how they do their science, who came up with this idea that is pretty much the same as Chris Chambers and his idea of registered reports. So the idea is that you should evaluate a manuscript solely on the basis of their relevance and their methodology. Given that they ask an important question in an experimentally meaningful way, they should be published regardless of the results. So this is basically saying, let's get rid of publication bias. The peer review system, papers sent to referees would contain only an introduction and a procedure section, and you may be supplemented with a brief description of how the data would be presented or analysed. But you wouldn't see the results. Only when the reviewers had rendered their opinions would you add the results. And then he says, an even better option would be to have contracted publication in this system, so the researcher submits his idea and experimental procedures to the editor prior to their execution. So you don't even do the study, you get your reviewer, editor and reviewer looking at your plan, at your protocol for what you plan to do. But then you're guaranteed subsequent publication if that protocol is approved. This is amazing because nobody took any notice of this in 1976, but actually it's now coming to pass with registered reports. This is Chris Chambers, and his registration revolution 38 years later was talked about in 2014. This is in The Guardian, mentioned it as a change in how science was being done. And it's pretty much the Mahoney approach. So classic publishing, what we're all used to, you plan a study, you do the study, you submit it to a journal, you then send it out, it gets sent out to reviewers, and you may go round and round a loop where the reviewers want you to make changes, and you may have several revisions, or it may get rejected at that point. But if you're lucky and you respond in a satisfactory way, it then is accepted and published. In registered reports, you have the same model, but the doing of the study is coming only after you've had the submission and the response to reviewers. So it's what Mahoney said in terms of what you submit is your protocol, in effect. It's a justification for why you want to do the study, detailed account of methods, and that is what gets reviewed. And then you do the study, and if you do what you said you were going to do, it will be published regardless of the results. Now, obviously, editors who adopt this model are going to be reluctant to do that unless the study is really methodologically very strong, because what they don't want is, say, an underpowered study that can't answer the question. So you're building into this a requirement for very strong methods. It's not the same as pre-registration, although it's very similar in some ways. Pre-registration could be regarded as a sort of lighter version of registered reports, where you're not contracting with a journal at all, but you can still register your study plan before you do the study. But then you just do the normal publication route, and there's no guarantee of publication. I've done pre-registration as well as registered reports, and I have to say reviewers are generally pretty positive if you pre-register, and I say there's some benefits to it. But I think registered reports are more effective for a number of reasons. What are the benefits? Basically, the principal benefit is that you get rid of the four horsemen of the irreproducibility apocalypse. There's no publication bias because the decision is made before the results are known. You can't engage in p-hacking without it being obvious, because you've specified what your variables are going to be and what your analyses are going to be before you've done the study. Similarly, your hypotheses have been specified. So if you do hacking, it's obvious that's what you're doing. And if you've got low power, you're going to be rejected, because no editor is going to want to commit to publish your study if the power is inadequate to test the hypothesis of interest. Now, it doesn't mean that you can't report unanticipated findings, but it means that you make this distinction that de Groot was very keen on between what is hypothesis testing and what is exploratory. So you would write up what you'd planned to do, but if you then found an amazing finding that you hadn't expected that suggested a really interesting hypothesis, that would also be included in your study, but it would be written up in a separate section, and you would be required, or you wouldn't be allowed to do the sort of hypothesis testing statistics on it. You would be more putting it forward as a hypothesis that then would need testing in another data set. So I want to say a bit about my experience with this and the pros and cons, but there have been massive objections to this from a number of people who've said this is all very well, but doesn't it just kill creativity and prevent serendipitous discovery? I mean, we all know that there have been amazing findings that nobody anticipated in advance. And if we expect some people say, well, if you only test things where you expect to find them, isn't it going to be very boring? The answer is really no, because there is no problem with exploratory analyses. You can still do them, but it's just that they're clearly labelled as such. So, I mean, people talk about, for example, there's a discovery of Hubel and Wiesel's discovery of orientation-specific neurons with receptive fields in the visual cortex, which was discovered by accident because they actually had a slide with a crack on it, and they found that when they put that slide up, the recording machine started to react vigorously, and nobody could work out why, and it was because it was responding to this line on the slide that was an accident. Now, if we said, oh, you can't report that because you didn't predict it, obviously that would be crazy. But obviously what Hubel and Wiesel would do would be to formulate a hypothesis on that basis that, hey, maybe this line on the slide is important, and then do further studies to test that and to demonstrate that this is the explanation. But it's not saying you can't do that. It's just saying, be very clear that this is not, you wouldn't go off. In fact, they wouldn't have been believed if they just said, well, we think this is the explanation, and hadn't done any more specific studies to test it. You don't generate and test hypotheses on the same data set, but you can certainly generate hypotheses if you're prepared to then go on and test them in a new data set. There's also this wonderful unexpected benefit. This is Hannah Hobson, who was my graduate student, who very bravely, she and I did our first ever registered report. She was a graduate student with me, and we were both very nervous about it, and she wanted to work on something that I didn't know anything about. Well, I knew a bit about it. I'd been working with electrophysiology and EEG recordings, but I hadn't looked at this phenomenon of so-called mu suppression, which was supposed to be measuring activity in the human mirror neuron system, so that if you see a gesture of some sort, you get reaction in the motor cortex as if you were doing that gesture yourself. So we thought we'd try this as a registered report, and Hannah submitted a quite complicated design, and the first thing that came back from Chris was, well, you've got to take out about half of what you're planning because it's too much, which was very good advice and is often what you get if you do a registered report. But we then got reviewer suggestions, which were fabulous, because we got suggestions for a number of controls that if we hadn't had, I think, and we tried to run this study and then send it out to review after we got the results, people would have said, well, you haven't controlled for this, you haven't controlled for that. And so we got suggestions for a number of controls that we should put in, which meant it took a lot of time, it was difficult, we were doing things that we hadn't done before, but it made the paper really good, we think. We're quite proud of this one. It was nail-biting because Hannah had limited time to finish her PhD before she went on to the next thing, but it was definitely well worthwhile for improving the quality of the study, and it was good for her to have this assured of publication. Often people say, well, particularly students, well, this is all very well, but I don't have the time, because if you're going to do all this in advance, you're going to get this refereeing and so on before you've even gathered any data. and you're under time pressure, isn't that terrible? But this is really what we found with Hannah's study, is that it looks as if you're taking more time, but it's really just when the time is used, because essentially what happens is that you save time at the end of the process, because if you've had this classic publishing, you do the study, and then at the point at which you're ready to submit to the journal, the reviewers start coming back saying, well, you should have done this, you should have done that, and you're going round and round, possibly wanting another experiment. At this time, quite often, if you're a graduate student or a postdoc, you're running out of money, you're running out of enthusiasm. I've put this line here for funding and enthusiasm, which are beginning to go down after you've done all this work. Other demands are often going up. And so you get into serious trouble. Whereas what happens with the registered report, of course, is that you have front-loaded the time. When you're planning the study, that all takes longer. But then the bit at the end, so with Hannah's study, when she submitted it, we'd done what we said we were going to do, and one of the reviewers did come back and say, well, it would be incredibly nice if you do this additional analysis. And she'd gone on to another job, and the additional analysis was incredibly complex, and Chris was happy to say to us, you don't need to do that. And indeed, what we were able to do was to deposit our data, which was required of us, and to say, yeah, that's a great idea for an analysis, but our data's there. If anybody wants to run it, let them run it. But we were not required to do that in a way that could have happened otherwise. So I think that in terms of time, this is actually more efficient, but it doesn't look like it when you're at the outset and panicking. I have to say also, if you do run out of time, you can stop with the registered report. So this is Abigail Bradshaw, who was another graduate student, and we tried a registered report which was rejected. The referees didn't like what we wanted to do, and we discussed whether we were willing to sort of go back and think about it again. But she was getting apprehensive. She again was a PhD student, limited time. But we thought, well, okay, we'll stop this as a registered report. But the beauty of it was that we still had the reviewer comments, which, hostile and difficult though they were, of course, were useful in helping us improve the study and anticipate objections later on down the line. So this again led to a study that was enhanced by having been put forward as a registered report, even though we didn't see it through as a registered report. The other benefit is you can't have this shifting of goalposts. You can't have this thing where you address all the reviewer comments and then people are always complaining about this on Twitter, that you've just done everything and then it goes and the reviewer suddenly thinks of another thing that they wanted you to do. So this is akin to what happened with Hannah, where the reviewer started to say, well, you should do this other very fancy analysis. And we were able to say, well, no, we didn't, that wasn't agreed in advance. So we could have agreed to do it, and had we had time and energy and so on, we would have, because it wasn't a bad idea. But it means that you can take some sort of control over what it is that you're required to do and not. The power issue is a really serious one, because people often do a power analysis and then get very depressed and say, well, it's all very well, I just haven't got the resources to do an adequately powered study. And often people don't have resources to look at, hundreds of people, for example, in human studies, or hundreds of animals, even worse. But I would say that this can be dealt with. I mean, it forces you to think hard about power, but it might lead you to improve your research design. If you do a lot of piloting and simulation, you may find ways to improve power that don't necessarily need much bigger sample sizes. For example, you may change your experimental design or use a measure that is just a better measure that is less noisy, and that will improve your power. But often, when I've done registered reports, I will do a simulation for power calculations, and it may mean that we just decide not to do what we originally wanted to do because we realise it's going to not be adequately powered, and that's just unfortunate. You can then, though, we've also done this, ended up saying what we really need to do is to join forces with another research group and have a collaboration and find if there are others who are willing to look at the same question. You can then end up doing a really meaty study that is going to have adequate power. So it forces you to think about it, and this isn't easy, but it is really important, I think, to be made to think about it at the point of planning, not only after you've gathered the data and then realised that you're not really adequately powered. So, to sum up, I think registered reports are really good for science because they give you a more credible picture of the state of evidence, because you just get rid of publication bias and p-hacking, and you can't really do these uninformative, underpowered studies. But I think it's also good for scientists because partly this very unexpected thing that peer review becomes much more positive. It's a positive source of advice, and peer reviewers are often much happier to advise on something where you haven't yet gathered the data than to start telling you what you should have done, which you haven't done, and which is, is this a fatal flaw? It's just all very uncomfortable to realise too late that you should have done something. You often get a lot more piloting and simulation, and that will improve the study design, and it gives you this control of the publication timeline, which is really important, I think, for early career researchers. What I'd like, a lot of people do come up with drawbacks and sort of questions about, is it really, or potential problems? And I thought we've got time for discussion. I'm very happy to discuss, scenarios with you, or your experiences, or things that may be good or bad about this. But other than that, I was just going to leave you with these resources. There's a whole section on registered reports on the Centre for Open Science, with frequently asked questions, which are answered. And then there's various talks by me, and I've got a YouTube course that's a beginner's introduction to simulating data, because I see simulation as going hand in hand with doing registered reports. But I look forward to some discussion, and thanks for your time.